So hello everyone, this is lecture 11 for the classical physics. In the last lecture I have given you some questions. Okay, so hope you managed to solve them. Else let me give you the solution. So this is our question. A particle of mass 1 kg, angular momentum this, and total energy this 3 joule is subjected to a central force field that is F equal to minus kr, where k is 2 kg per second square. And which of the following statement is true? So we need to find these statements. So let's see. First, this force is given, so we can find the potential. So let's see that at energy 3 joule, what kind of curve we will get, means what kind of orbit we will get. So first we need to find that, only then we can decide that it will be circular or elliptical and what radius and where it will move and what kind of path it will have. So all we get only after if we know about the trajectory. So let's see about this thing first. So from this force we can find the potential, that will give you kr square by 2. Okay, so how we can find this? So remember, this mass is 1 kg, k is 2 and f is this. So first let's write the equation. We know about the effective potential. Let's see the graph first. So force is this given, and from this force we can find the potential, that will be minus fr dr, that will give you kr square by 2. So we have Vr, and we know about this is effective potential, sum of Vr plus L square over 2 mr square. So now we will plot this curve. So we will do is by just directly looking at these curves. So for 1 upon r square, this kind of curve we will get, this first one, this dotted curve we will get for this. And for this r square we will get a parabola, okay, because we equal to r square terms. So we'll get this kind of parabola. Now we will superimpose and see what kind of curve we will get. So first it will dominate, and up to here, then this second curve will dominate, and we get this kind of curve. Okay, so this will be our superimposed curve. Now to see whether it will be elliptical or circular, first we need to check what is the energy at this point. Okay, so this is our stable equilibrium point, so we need to see the energy. So how can we find this? So first we need to find this point, the distance of this point, then we will put it in the potential value, means this effective potential value, and then that's how we can find the energy, because at this point the radial kinetic energy will be 0, so this effective will be total energy equal to. So that's how we can find. So let's see first find this point at which it will be circular. So it will be find it by the direct formula, del V effective divided by del R equal to 0. So after solving this, you will get R naught equal to 1. After solving this equation, differentiate it with respect to R and put it equal to 0, you will get R naught equal to 1. Now the V effective at R naught equal to 1, put R as 1 and L is given, that is root 2, and K is also given, that is 2. So after substituting the value, you will get V effective as 2 joule, and V effective is equal to total energy at this point, okay, because of radial part is 0. So energy at this point is 2 joule, but the given energy was 3 joule. So now we know that this particle is not here and it is somewhere above it. Okay, so definitely it won't be circular orbit, because the circular orbit has energy 2 joule but total energy is 3 joule. So now this 1 joule extra energy can be taken in two ways. Either it can give you a proper elliptical orbit, or it can give you a oscillatory motion in the circular orbit, as we already discussed about this. Means either we can get something like this, okay, or we get a proper ellipse. Okay, so we need to find these r1 and r2, they will be same. Means if this is our circular orbit, then this will be your r1, and this maximum will be your r2. And here if you talk about, then this will be your r1, this will be your r2, maximum and minimum distance. So it won't be circular but this. Okay, so let's find the values. So how we can find? Now put total energy equal to, so it is definitely above this point, so we'll have two turning points. So total energy will be at turning point, it will be equal to V effective. So V effective is this, and energy is 3 joule given. So just substitute all the values in this equation. E will be 3, L is root 2, so it will give you 2 here, and M is 1, so 2 r square plus r square. Okay, K is 2, so it will cancel out. Now from this equation, it will give you a quadratic equation in terms of r square. So you can find the value of r square, that will give you this value, and from here you can get this r1 r2, that will be 3 plus root 5 and 3 minus root 5 by 2 and under root of that. Okay, So after solving this equation, you will get these two values as your radius. So this will be your maximum radius and this will be your minimum. So for ellipse, this will be your major axis, semi-major axis and semi-minor axis. And if you are having the oscillatory motion, then you already know that A and B part, and that will be R1 is this and R2 is this. Okay, so which option will be correct then? This one. The particle is bound within the annular region described by two circles. R1 is equal to this, R2 is equal to this. Because in options the ellipse is not given and it is not described about the minimum and the minor and the major axis. So only this option is correct. Because this option can also be correct. Particle is bound within annular region described by the two particles, but this radius are not same as we get. But in C option we are getting the same answer. So that's why this is the correct answer. Okay. So now let's discuss the second question I have given you. So this was the question: particle of unit mass move in a potential this if the angular momentum of the particle is given. Which statement is true? So first we need to plot this curve also. First let's plot the V effective for this also. So V effective is nothing but again this L square over 2mr square minus V naught exponential minus R square. Now you can plot this curve directly by just seeing this curve. Means first plot for the 1 upon R square. So for R tends to 0, this whole term will tends to infinity. So this will go like this to infinity, and we will get this kind of curve for this V naught over R square. This kind of curve we will get for this term, and using this value L equal to 0.5 under root V naught square will give you 0.25 V naught, and 0.25 divided by 2 will give you V naught by 8. Okay, and M is 1. Okay, so that's how you can write this equation in this form. Now see, this will give you this kind of form. This will tends to infinity when R tends to 0, and here it will gives you 0. Okay, when R increases, this value tends to 0, and when R tends to 0, this will go to infinity. But if we plot this is R negative, so it will go in the negative side. So for R equal to 0, this will give you minus V naught. So this will start from here, and it is exponential decay, so it will go like this and decay fast. So we need to superimpose this curve and this curve. So how we can superimpose? See, this curve is coming from infinity, so initially this value is very higher, so this will dominate. So but it is coming to down very fast, so it will go something like this curve. Initially it start from here because of this infinity term, and it is just minus V naught. But as we come somewhere here, so now it is V naught by 8 and it is V naught. So this will start superimposing, and that's why it goes somewhere negative. Okay, negative. Now this is an exponential term, means this is an exponential decay, so it will go very fast. Decaying is very fast. So again in this region, this will dominate again. This part will dominate again because this is exponentially decaying. So first reason is this dominating this part, then second this is dominating, that's why it is going like this. Now this is again dominating, so it will go like this and it tends to 0. So this curve we will get. So now from the options or from this graph directly we can see that there is this one stable equilibrium point, not two, only one is there. And if this is R2 is greater than R1, okay, and at R2 we will have an unstable equilibrium point. So from option directly we can see there is one stable equilibrium point at R1 and one unstable equilibrium point at R2 greater than R1. So this option will be correct. Okay, so that's how sometimes you need to just directly observe the values and see, make this graph, because if you try to draw this manually by finding the values R at which we are having unstable equilibrium point and stable, you will get a very long calculation and it won't be easy to solve, very hard to solve. Okay, you can try this, but you won't be able to solve it without any software. So that's how you can plot this. Okay, now let's see one more question. In the attractive Kepler's problem described by the central potential this, so we are talking about a planet where k is a positive constant, a particle of mass m with a non-zero angular momentum. So particle of mass m with a non-zero angular momentum can never reach the center due to the centrifugal barrier if we modify the potential to this one finds that there is a critical value of the angular momentum Lc, below which there is no centrifugal barrier. This value of Lc is. So what question is trying to say is, means there is this particle rotating, planet is rotating around the sun, so it never goes to the sun, means it never meets the sun. So what is the reason behind that? So you know, in the circular motion this radial component is 0, but we are having something, this tangential component of velocity, that is v theta we define, and we get this angular kinetic energy was L square over 2m r square. So if this becomes 0, still we are having some kinetic energy due to this. So this acts as a centrifugal barrier. This won't let the particle to coincide with the source. Okay. So this is our barrier. So if we are having this potential, then this kind of curve we will get for this. Okay. So this curve we will get. So this is the only factor which never lets the planet or particle to coincide with the source, and we call this as centrifugal barrier. So if we discuss about the turning points, let's consider this curve. Okay, this is any curve possible. So here in this region you will have the bound motion, it is oscillating, and this is never coming to this 0. Okay, means this is oscillating between these 2 points, but it is not, r is never becoming 0. So let's see what is the reason behind it. So we know from the equation at the turning points radial component is 0, so we will have total energy equal to L square over 2m r square, and for planet we have minus k by r as our potential. So let's try to solve this equation in terms of r. So we'll get a quadratic equation something like this, r square r L square. So if you find the value of r from here, you will get this equation. Now see, we need to make this r 0, only then the particle can coincide with the source. So let's see what is stopping us. So to make this equation 0, the only possibility to make this 0 is put L square equal to 0. Only then you will get 2mk here, and plus value of 2mk minus 2mk will give you 0. Otherwise you can't make it 0 any. Okay, there is no way to make it 0 other than this. And we know this L square is not 0, means L is never be 0. We can't make L equal to 0. So that's why the particle will never meet to the source. Okay. So we always have this radial tangential component, that is our angular kinetic energy. Okay, so that's why it's not possible. But now the question is saying that we change the potential. Now potential is minus k by r minus beta by r cube. Okay, so what is the critical value below which it can meet this source? Okay, so we need to find that critical value of L. Okay, so how we can decide that what is the critical value? So when this radius, just as we found this here, so when this becoming 0, either this can become 0 or imaginary, only then is possible that this r will be, means the planet will be meeting the source. So here we see that this is not possible. So let's see if they change the potential, what can be the critical value. Now potential is Vr equal to minus k by r minus beta by r cube. So this whole thing was just to make you understand this concept. Okay, so now the solution starts from here. So Vr equal to this, now we change this potential to this. So at the turning point we have this total energy equal to this. Now let's find the stable equilibrium point. Okay, because to have to meet to the center, you need to have a motion which is bound. Only then you can see that if it is meeting to the center or not. Okay, so to have a bound motion, so we need to find this stable equilibrium point above which you will have this motion. So let's find this point. So for that, just use this equation, del effective by del r equal to 0, and after differentiating this equation, find the value of r. Okay, so now we will get this by solving just this, we get r equal to this. Okay, so now let's check. This r can't be 0, this can't be 0 or can't be less than 0, means it can't be less than 0 or it can't be imaginary. Only then we can have the possible motion, bound motion. Okay, so we need to find the value of L, that critical value of L, above which this will have the bound motion. So let's say if this value becomes equal to this, so what we will have? We will have L square over 2km. Okay, and if this value is less than this value, then we will get the imaginary term here. Now this will be iota time. Okay, means iota will get here, so we can't have this imaginary term here, and this should not be equal to 0. So we can see that so this value should be greater than this value, so L4 should be greater than this to have the possible values of R. Okay, so less than this we will have a imaginary values and the 0 values and all. So the critical value for L can be find from here, that L4 should be greater than this and L should be greater than this, and so we'll call this point as critical point. So this will be your answer. This is C part, 12 km square beta 1/4. Yes, it is your C part. Okay, so it was the question to bring you the information, all information we can draw from this question. This is very important. Okay, so remember this, that why this never meet to the center, because of this condition, this L can't be 0. So if potential is changed, then you can find the critical value above which this will be a bound motion. Okay, so let's see the last topic for the today's lecture, that is Virial theorem. So this is a topic of statistical mechanics actually, but we can use the results here. Okay, so I will just give you the brief idea. You will study more when I come to the statistical mechanics. According to this theorem, the average kinetic energy of a system of bound interacting particles is related to average potential energy as follows. So if we have a system, a large number of systems, and there are interacting particles, so they have a average potential energy as delta V. Okay, this is our average potential energy. So you can find from this value the average kinetic energy, that will be n+1 divided by 2. Now what is n here? So if potential energy is given in this form, AR n+1, then you can find T as just putting n here, then you can find the T. So this is a Virial theorem, is nothing but relation between potential energy and kinetic energy in a system. Okay, for the system of particles, and total energy is nothing but sum of kinetic energy and the potential energy. So this is our Virial theorem. So what kind of question can we ask in the classical physics based on this? Let's see. Consider the set of particles which interact by a pair potential this. So potential is given where R is inter-particle separation, A is greater than 0, is constant if a system of such particle has reached Virial equilibrium. Okay, means Virial equilibrium, now they satisfy the condition we draw for the system. So we need to find the ratio of kinetic energy to the total energy of the system. So kinetic energy can be find here, it will be R n+1, n will be 5. So if you put 5 here, it will give you 3V. So kinetic energy will be 3 potential energy, and total energy will be 3 potential energy plus potential energy will give you 4 times potential energy. Okay, so this will be our kinetic energy. Kinetic energy will be 3V, and potential energy is V, so total energy will be 4V. So we need to find the ratio. So kinetic energy was 3V and total energy was 4V, so 3/4 will be your answer. Okay, that's how you can find and use this equation. So remember these results, very important. So next I will start with the gravitation. Thank you everyone.